Hello everyone, in today's video we're going to cover the properties of logarithms or log rules as they're commonly referred. Note that this is a playlist on math fundamentals, so it's all the classics in mathematics that come back often. We're going to learn quickly the theory of logs and how you should think about them, or how you can think about them to remember them first of all, but also build a bigger intuition of what they are and how they work. Then we're just going to cover the log rules quickly, and we're going to cover two examples together so you get a chance to practice a bit. So 2 examples isn't that much, so that's exactly why we're going to do the other exercises on your own, but you're going to have this solution set to practice with. The solutions will be posted in the description below, and without further ado, let's get to it. If you're new here, my name is Olivier and I'm a certified math and physics teacher in Ontario who is currently doing a master's in statistics at Carleton University. Here I pulled up the student version of these notes in OneNote because it's easier to write with. Speaking of writing, I have a broken right hand, so the writing might be a bit worse than usual and you might hear some Velcro sounds because that's just the sound of my brace. The main thing you need to realize is to ask yourself what logs are for. So logs are for when we have something like this 2x is equal to 5, and we're trying to solve for x. The main difference is if we have 2x is equal to 5, we know what to do. We can just divide by 2, right? So then it would be 5 divided by 2, which is 2.5, and then you can kind of plug this 2.5 back in, and 2 times 2.5 does equal 5. But this is not as obvious. So the main thing you need to realize is that logs are used to solve for an unknown, so an x, exponent. If you're not sure what exponent rules are and how they work, make sure that you watch the previous video that you're going to see pop up in the top right corner. In log rules, we have this big equivalence here, which says that if you have a to the x is equal to y, we can take the log base a of both sides. So let me write this here. If we have ax to the x is equal to y, we can take the log base a of both sides. So it'd be log base a. And note that there's a rule that when you have log base of the same thing, you can bring down the exponent. We're going to see that a little bit below. And then log base a of a simplifies. So really you get that you bring down the x and then this will cancel. So you're just going to have x is equal to log base a of y. And that's what we have in this equivalence here. So that's why. Let's say we're trying to solve the yellow equation to 2 to the x is equal to 5. It's 2 to the what is equal to 5. So for example, if you have 2 to the 1, we know that's 2. If you have 2 to the 2 to the 2, that's equal to 2 times 2, which is 4. So that's still not 5. It's close to 5. So if we go one more higher, so that would be 8. So that's way more than 5. So we know that it's 2, like x is somewhere between 2 and 3. So I can write that. So it's somewhere between 2 and 3. So let me write this in red. So between 2 and 3. And again, the solutions are all going to be typed out in the description below, so don't worry about my writing. And we know it's probably going to be closer to the 2 than the 3 because this is 4 and 3 is 8. And the whole point of logs is to bring down the exponent. So it's to bring down the unknown exponent. So the exponent. If you just use the equivalence, we would get x is equal to log base 2 of 5. Now this you can compute in your calculator. You can plug it in directly if you have a log base a button. But if not, you can just do log 5 divided by log 2, and that's going to work because, as we're going to see a bit later in the log rules, this is a change of base formula. This is the same thing as just writing log base 2 of 5. And when you compute this in your calculator, I'll let you do it, but I'm pretty sure, correct me if I'm wrong in the comments, it's somewhere around 2.32. And then you can check with your calculator. So if you put 2.32 in there, you should get something very close to 5 here. And you could check it. Obviously, it's not going to be exactly 5 because we're rounding. But if you keep the whole thing in your calculator, it should give you exactly 5 or very, very, very close to 5. But now let's cover the actual log rule. As you recall, in exponent rules, when we have a multiplication, we add the exponents. Well, it's kind of the same thing. When we have two things which are multiplied inside the logarithm, well, we can add them and take the same base for them. So that would be the multiplication one. And then similarly, if we have a division, we just subtract those two logarithms. So division and subtraction often go together, and multiplication and addition often go together. And here is the drop-down rule that I was talking about. So that's the point of logarithm. Note that we brought down the y here. That's why it goes there. And then when we have base a here, these two would cancel, and that's why we'd just be left with y, and that's kind of the whole point of logarithm, is to solve. Because when we have log base a of a, that's just equal to 1. And note how I'm saying log base a of a, it's like base a, so that would be kind of like a over a, and that's how you can kind of remember that's the base, so it's in the basement. If we bring down the x here, it'd be x times log base a of a, these would cancel and you'd just be left with x. Log base a of 1 is 0, and that's because if you graph log base a of x, it's going to look something like this. And every time when x is 1, you're going to have y is equal to 0. Now this is a important rule right here. If you have a to the log a, these cancel as well. So that's kind of like if you have log base a of a, these cancel and give you 1. Well, these cancel and give you whatever's inside that log. So you're just going to be left with x here. This one is e to ln x. These cancel. Why? Because ln is log base e of x. So if we move on to this rule here, we have that ln is the natural logarithm. Ln of x is log base e. So that's the key thing. Ln is really log base e, and e is ish 2.71. It's kind of like pi is ish 3.14. E is just a number, and it's called Euler's number, and it's a number that appears very often in nature, just like pi does. So that's why this is x. It's because we have 2.7 ish log base 2.7 ish of x. So then these cancel, and you're just left with x. This is the change of base formula that I mentioned earlier. We can change the base by putting it here, and the b, you can invent a new base. So earlier when we change base, if I just scroll up, we had 10 here, that's b, and then a was the base. So a, I'll put it in yellow, a was the base that we had here. On the right is just a particular case of the change of base formula, and that's because we would have log base b of b, and log base b of b is simply 1. So that's why we get this 1 here. So don't worry too much about this one. It's better to learn the general rules, and then the particular cases will figure themselves out. And this is an important note. So when we don't write anything, it's really log base 10. So in your calculator, it's probably log base 10. And then if you have a log base 8, then you can play around with it by yourself. But by default, it's log base 10. So that's what I meant here by the change of base formula. You can just type in log 5 divided by log 2, because we can use the change of base to compute log base 2 of 5. So that's enough for the rules. Let's do 2 examples together, and then you're going to practice on the exercises by yourself. And don't worry, the solutions are in the description below. For example A, we have log base 2 of 3 plus log base 2 of 5 minus log base 2 of 30. Note that they're all log base 2, so it's kind of like exponents. We can use the rules because they all have the same base here. Generally speaking, we go from left to right. So I'm going to focus on the first two. We have an addition here. So we're going to combine all these logs and try to do something with them. We have an addition, so when we have an addition, it usually goes with multiplication. So we're going to multiply the numbers on the inside. So it'd be 3 times 5, which will be 15, then minus log base 2 of 30. So I'll just, instead of writing a new line, I'll just erase this and I'm going to write 15. Okay, so we have log base 2 of 15. Now we have a subtraction. So then that means that we divide, right? So we write log base 2 of 15 over 30. 15 over 30 we can simplify by dividing the numerator by 15 and the denominator by 15 as well. So then that would be 1/2. And note that we can even simplify this further. A lot of people would stop here and that might be fine. But in this case, there's something that is a lot better, right? We have log base 2 of 1 because it's a division minus, so when it's a division, it goes with a minus, right? So log base 2 of 2. So I think you see where I'm going here. The log of 1, we saw from the graph, that log looks something like this. So log of 1 is always 0. So when x is 1, and then this is log base 10 of x, log of 1 is 0. So we have this is 0. And then minus log base 2 of 2. We saw that log base a of a is 1. So we have 0 minus 1, which is simply -1. So this whole ugly line here, if you plug this into your calculator or in Desmos or anything like that, you'll just get -1, which is pretty incredible. For b, we have log base 9 of 27. So what we need to ask ourselves is, we're trying to get the same bases. So really it's 9 to the what is equal to 27. 9 to the 1 is 9. 9 to the 2 is 81. It doesn't go like that, right? But we notice that 9 is a multiple of 3 and 27 is a multiple of 3. So that's usually when we try to use a change of base approach. So we put the new base as the thing that it's multiples of. So it's a multiple of 3. So I'm going to just do it like this, and we have 27. And note that the base 9 goes in the basement. That's one way to see it. So now we can make the same bases approach. So we have log base 3. 27 is 3 to the 3. Because 3 times 3 is 9. 9 times 3 is 27. So we have 3 to the 3. Over log base 3 is 3 squared. So really now it's just a matter of simplification. We can use the drop-down rule. So if we simplify, it would be 3 log base 3 of 3 over 2 log base 3 of 3. Log base a of a is just 1, so really we just have 3 over 2, and that would be 1.5. So note that I created these examples that they simplify nicely. In the first one we got -1, and here we get 3 over 2. So they simplify nicely. They might not always, but the whole point of logarithms is that you can solve these equations a lot better. Now it's your turn to do a little bit of practice. You have 6 or 7 examples of logs here. I added a Khan Academy link, so you can always do more research if you need extra help. If you've enjoyed this video, make sure to check the other math fundamentals video that are made just for you. The best way to support the channel right now is to hit the like button, hit the subscribe button, and really it's to share this video with your friends and anyone who you think might be useful. As always, thank you for watching, and I'll see you next time with Do the Work.